Welcome to another module in this massive open online course on MMSE estimation for wireless communication systems. So, we are looking at the linear MMSE estimator, that is the linear minimum mean squared error estimator, or also known as the LMMSE estimator, and we are looking at finding the optimal weighting vector C bar, that is the combining vector C bar, and we said that if we have a function f of C bar, a function f of the vector C bar, then the derivative with respect to C bar, that is this is a function of C bar, and its derivative with respect to C bar will be dou f by dou C 1, dou f by dou C 2, so on dou f by dou C n, that is derivative with respect to each component. So, naturally this is an n dimensional vector, where n itself is the dimension of this vector C bar. For instance, let us take an example. Let us consider a simple scenario where this f of C bar equals this function is k, this function of C bar is k, which is a constant, then dou f, then df, in fact this df we can write here instead of dou, since we are considering the derivative, this df by dC bar. So, I will write df by dC bar, that will be d of, that will be equal to, let us write it over here, your df by dC bar will be partial derivative of k with respect to C 1, derivative of k with respect to C 2, derivative of k with respect to C n, and each of these is equal to 0, since this is the derivative of a constant with respect to C 1, C 2, C n, these are, therefore, each of these are equal to 0, therefore, this equal to 0, which means df by dC bar is equal to 0. Okay. The derivative of this function f, if f is a constant, right, this we already know this, right, it is very straightforward. The derivative of a constant with respect to a scalar quantity is 0, and on now we are naturally extending to a vector, we are saying that this derivative of this constant with respect to this vector is 0. Let us now consider a slightly more advanced scenario, slightly more complex scenario. Let us consider a vector, an inner product with a vector. So, let us say u is a constant vector, let u bar be a constant vector, then the inner product is u bar transpose C bar, which is the row vector u 1, u 2, so on up to u n, times the column vector C 1, C 2, so on up to C n, and this is equal to u 1 C 1 plus u 2 C 2 plus u n C n. Okay, we already said this u bar, this is a constant vector. Okay, so, this is my u bar transpose C bar. Hence, the derivative of this quantity, now this u bar transpose C bar with respect to this quantity with respect to the vector C bar. Now, you can see this is nothing but the derivative of u bar transpose C bar with respect to, well, with respect to C 1, the derivative you can see is u 1 with respect to C2 the derivative will be, partial derivative will be U2, so on with respect to Cn the partial derivative is Un, and therefore, this is equal to nothing but the vector u bar. Therefore, we have this interesting result that the derivative of u bar transpose C bar with respect to C bar is u bar. Okay. We have this result over here. The previous result we have is with respect to the constant, that is the derivative of this constant, correct. So, we have this derivative when this f of C bar is the constant, derivative with respect to C bar that is equal to 0. Now, of course, you will also see this u bar transpose C bar, this is also equal to C bar transpose u bar, correct. This is also equal to C bar transpose u bar, which is basically your row vector C1, C2, Cn times the column vector u1, u2, un, and this is therefore equal to C1 u1 plus C2 u2 plus Cn u1. So, we have u bar transpose C bar is also the same thing as C bar transpose u bar. In fact, these are both scalar quantities, so they are equal to the transpose of each other, and in fact, C bar transpose u bar is basically nothing but the transpose of u bar transpose C bar. Okay. And therefore, naturally, if we take the derivative, we have the derivative of C bar transpose u bar with respect to C bar will be equal to the derivative of u bar transpose C bar with respect to C bar, and we already know this derivative of u bar transpose C bar with respect to C bar, this is equal to u bar. Okay. So, we have this principle. Now, let us consider the second order derivative, that is the quadratic function of C bar. That is, we have considered the constant, we have considered a linear function of C bar where it is weighted by the combined vector u bar, that is u1 C1 plus u2 C2 so on up to un Cn, that is the u bar transpose C bar or C bar transpose u bar. Let us now look at a quadratic function of C bar, that is a function which involves squares of the terms of this vector, squares of the components of this vector C bar, and that function is basically your C bar transpose P C bar. This is known as a quadratic form. This is known as a quadratic form, correct. And further we are considering interesting scenario where P is equal to P transpose, that is matrix P is symmetric. Further, we are considering a scenario where this matrix P is symmetric, that is P is equal to P transpose, and it can be shown that in this scenario it can be shown that the derivative of C bar transpose P C bar with respect to C bar, this is equal to twice P C bar. This can be shown, all right. We will not show this explicitly over here, but the derivative of this quadratic form, the derivative of C bar transpose P C bar with respect to C bar is equal to twice the matrix P into C bar, where this matrix P is a symmetric matrix, that is P is equal to P transpose. Okay. So, now we have all the basic results related to the vector derivative, derivative of this function of this vector C bar with respect to C bar. Let us now go back to our MSE, the mean squared error cost function, as a function of this vector C bar, combining vector C bar, differentiate it, set it equal to 0, to find the optimal vector C bar which minimizes the mean squared error. That will give us the MMSE estimate, and since it is linear in nature, that is the linear MMSE estimator or the LMMSE estimator. Okay. So, now if you look at our MSE as a function of C bar, recall we have already derived this previously. The MSE as a function of C bar, this is equal to your C bar transpose R y by C bar minus twice C bar transpose R bar y h plus R h h. Now, we have to differentiate this MSC, which is a function of C bar with respect to the vector C bar. So, this is a vector derivative or also basically known as the gradient, okay. And this is equal to the derivative with respect to C bar of C bar transpose R y by C bar minus twice C bar transpose R bar y h plus R h h. Now, you can see this will be equal to, now look at this, this is of the form, well this is of the form C bar transpose P C bar. So, its derivative will be twice P, here is the matrix R y y. So, it will be twice the matrix R y y times C bar minus, this is of the form C bar transpose U bar. So, it will, its derivative will be 2 C bar transpose U bar, derivative is U bar. So, that is R bar y comma h, and in fact, R h h, this is a constant k. So, the derivative of this with respect to C bar equals 0. So, this derivative with respect to C bar of the MMSC is twice R y by C bar minus twice R bar y h. This is the derivative of the MSC with respect to this is the derivative of the MSC with respect to C bar. This we have already seen, okay, DMSC with respect to DC bar. Now, what we have to do, remember, to find the optimal C bar, I have to equate this derivative to 0. So, now set this derivative to 0 to find that C bar which minimizes the MSC, that will give us the MMSC, the minimum mean squared error. So, set equal to 0. So, set equal to 0. To find C bar which minimizes the MSC. This basically implies that your this quantity, the derivative 2 R y by C bar minus 2 R bar y h is equal to 0. This implies that R y by C bar equals R bar y h. This implies C bar equals, this is a system of linear equations, therefore, C bar equals R y y inverse R bar y h. Okay. So, this is now the vector which minimizes the MSC, that is the yields the minimum mean squared error, correct, and this is the combining vector C bar, that is C bar equals R y y inverse R bar y h, okay, that is the that is the expression now we have finally derived for the combining weights. Remember what is C bar? C bar is nothing but contains the coefficient C1, C2, Cn, such that if you form C1 y1 plus C2 y2 so on up to C1 Cn yn, that yields the linear estimate which minimizes the mean squared error, correct. So therefore, and now also to recall what is RYY, just recall briefly in case it is not already clear. RYY equals expected y bar transpose, and this R bar YH is the cross covariance, that is expected y bar into H, that is the cross covariance, okay, between the observation vector y bar and the parameter H, correct. And therefore, now what do we have? The optimal MMSE estimate H hat, this is C1 y1 plus C2 y2 plus so on Cn yn. This is the LMMSE estimate. Remember, now we are in the LMMSE domain. This is the LMMSE, which is equal to C bar transpose y bar, and we already derived the expression for C bar. C bar is R y inverse R bar YH, correct. This transpose times y bar, which is equal to, now look at this, this is AB transpose. We will use the property that AB transpose equals B transpose A transpose, to write this as R bar YH transpose RYY inverse transpose into y bar. Now observe two things. One is this R bar YH is expected value of y bar into H, and R bar HY is expected value of HY bar transpose, and therefore, if you take the transpose of R bar HY, now if you look at this R bar HY transpose, that is equal to expected HY bar transpose, which is equal to expected value of y bar transpose into H, because H is a scalar quantity, H transpose equal to H. So, this is equal to R bar H, this is equal to R bar, of course there has to be R bar H y expected value H y bar. So, this will be y bar into H. So, this will be R bar into YH. So, R bar HY transpose is R bar YH, which means R bar HY is equal to R bar YH transpose. Okay. So, this is the relation between these two quantities, they are transposers of each other. R bar HY is the transpose of R bar YH. Okay. So, therefore, and further now if you look at this quantity RYY inverse transpose, realize that RYY equals expected y bar transpose, this is a symmetric quantity, correct. Implies RYY equals RYY transpose, since it is symmetric, and also naturally if the matrix is symmetric, its inverse is also symmetric. This also implies RYY inverse is RYY inverse transpose, and therefore, I can basically simplify this quantity here. First, instead of RYH transpose, I can use R bar HY. RYY inverse transpose is the same as RYY inverse. So, I can write this as RYY inverse y bar, and this is the expression for the LMMSE estimate, and this is the succinct as well as very interesting expression. So, let me rewrite it again. The LMMSE estimate is finally derived as your the LMMSE estimate is given as h hat equals r bar h y into r y y inverse into y bar. This is the expression for the LMMSE estimate. And if you notice this, you will observe something very interesting. Let me just, if you notice this, you will observe something very interesting. This looks exactly identical to the expression for the MMSE estimate, that is a minimum mean squared error estimate, but realize something very important. This is not the MMSE estimate, this is the LMMSE estimate. Realize that the MMSE estimate was derived assuming that the observation y bar and the parameter h are jointly Gaussian. So, what this means is something very interesting. If h bar, if y bar and h are jointly Gaussian, then the MMSE and the LMMSE estimate are the same. Otherwise, this expression, that is r bar h y times r y y inverse into y bar, is only the LMMSE estimate, that is it is only the optimal MMSE estimate in the class of linear estimators, but it is not the general MMSE estimate. Okay. The general MMSE estimate will still be given by the quantity expected value of h given y bar, that is expected value of the posterior probability density function, which may be difficult to find. That is why we embarked upon this LMMSE approach. So, the point to remember here is for Gaussian or for the scenario for h comma y bar jointly Gaussian, your MMSE is identical to LMMSE. However, for arbitrarily distributed h comma y bar, this is only the LMMSE estimate, not necessarily, in fact generally this will not be the MMSE estimate. So, generally speaking this will not be the MMSE estimate. So, I am just going to not the MMSE estimate. So, what you can see is if the probability density, joint probability density function of the observation vector y bar and the parameter h is Gaussian, then this expression r h y into r y y inverse into y bar is basically the MMSE estimate itself. Of course, if the MMSE, then it is also going to be the it's the MMSE, and also it is linear, so it is naturally the LMMSE also. But however, for arbitrarily distributed h and observation vector y bar, this is simply the LMMSE estimator, that it is only the lowest, that is it is only the estimate which yields the lowest mean squared error or the minimum mean squared error amongst the class of linear estimators, but it might not be, because there might be other non-linear estimators which might have a lower which might yield a lower mean squared error, but we are not interested in finding them because finding them is very complex. So, we are settling for the best estimator amongst the class of linear estimators, and we are calling it the LMMSE estimate or the linear minimum mean squared error estimate. Alright. So, that is the important thing to keep in mind, that is for this scenario where this h and y bar are not jointly Gaussian, since evaluation of the MMSE estimate is complex, we have evaluated a simplistic LMMSE estimate. right, which is basically the optimal amongst the class of linear estimators. Okay. All right. So, this is the expression for the LMMSE estimate, which we are going to invoke again fairly often, and this is an important result because the LMMSE estimate is widely used in both signal processing and communications, and it is used in several applications in signal processing and communications. All right. Now, let us also compute the resulting MMSE or MMSE of the LMMSE or MMSE of the LMMSE estimator. And this can be derived as follows. Again, we have the MSE as a function of C bar. Recall, we already derived that MSE as a function of C bar. This is C bar transpose RYY C bar minus twice C bar transpose R bar YH plus RHH. This is nothing but sigma h square, RHH is nothing but sigma h square. So, now I will substitute the expression for C bar, substituting the expression for C bar. C bar, remember C bar equals RYY inverse R bar YH, and in fact C bar transpose this is equal to R bar HY into RYY inverse. So, we can substitute that expression here, and therefore, this becomes well, C bar transpose is R bar HY into RYY inverse into RYY into RYY inverse into R bar YH minus twice C bar transpose, that is minus twice R bar HY RYY inverse into R bar YH plus RHH, which is sigma h square. And now, you can see this RYY inverse and RYY cancel. So, we are left with R bar HY RYY inverse into R bar YH minus twice again the same quantity. You can see interestingly we have the same quantity R bar HY RYY inverse into R bar YH plus sigma h square, and therefore, finally, this gives the sigma h square minus R bar HY RYY inverse R bar YH, and this is equal to the MMSE of the minimum mean squared error of the LMMSE estimator. This is the expression for the minimum mean squared error, that is your sigma h square, and you can also write this as this is also equal to your RHH minus R bar HY RYY inverse R bar YH, and let us again just write the various quantities again. Your RHH is expected value of h into h, that is x square. R bar HY equals expected value of HY bar transpose, which is R bar YH transpose, and RYY equals expected value of Y bar transpose, and these are the different quantities, and this is the resulting minimum minimum mean squared error of the LMMSE estimate. Again you see that it has the same expression as that of the minimum mean squared error for the Gaussian, and that is naturally the case because for the Gaussian the MMSE and the LMMSE are the same. Okay. So, both the LMMSE estimator and the MMSE estimator yield the same mean squared error, the same minimum mean squared error. However, for the non-Gaussian probability density function of H and the observation vector y bar, this is simply the MMSE minimum mean squared error yield which given by the linear MMSE estimate, that is the estimator which is best amongst the class of linear estimators. The actual MMSE of an optimal MMSE estimator, if that can be found, that the MSE of that will naturally be lower than this, because this is simply the linear MMSE estimate. Okay. So, that is something to keep in mind, alright. And of course, here we have considered a simple scenario where all these quantities are 0 mean. It is important to keep in mind that this basically is based on the assumption that all the quantities, the parameter h, the observation vector y bar are basically 0 mean, alright, and this can also be extended to scenarios where these are not necessarily 0. So, that completes the derivation of the LMMSE estimator, and we are going to look at applications of this LMMSE estimator in the subsequent modules. Thank you very much.